All right. So quick reminders. So homework D2, that's the one with random variate generation. 2 questions, random variate generation. Basically, one where you have to derive a CDF from a PDF, another one where you have to, and then invert the CDF and generate some random numbers, and another one where the CDF has been given to you and you have to invert it. And there's a couple little tricks that are involved there. So it's technically due today, but there's no late penalty until the availability window runs out, which I think is Saturday, if I do the math right there. So the effective due date is Saturday, but just did it this way to respect the kind of like late policy on homeworks, but I'm just relaxing the late penalty so you can turn it in all the way up until I think Saturday without any penalty, but then you can't turn it in after that. The solution set will go live Sunday. So you can see Canvas for more details. There are some helpful hints included in there. There's also some samples that are on Canvas that hopefully can help you with. When you do the histogram, make sure you histogram your random variate X and not the random numbers R. So sometimes that happens. Sometimes it's just an accident. You grab the wrong column when you do the histogram and you end up getting just a pure uniform, like a box from 0 to 1. So if your histogram looks like a box from 0 to 1, then you probably graph the wrong numbers. And so make sure you're graphing the histogram for the random variate. As a hint, this random variate will have 2 sections that are disconnected by kind of a lull. So if you've done it properly, you should get kind of something on the left and then an empty spot and then something on the right. I won't share exactly what those shapes are, but that's kind of your hint to know that you're kind of doing this right. Make sure that your submission is your primary submission. All of the important info that's needed for grading is in either doc, docx, or PDF format. So it's great if you want to upload your Excel spreadsheet of all of your of all the numerics that you did to generate the histograms, but the actual histogram, like that graph, should be in the doc, docx, or PDF, whatever that main document is that you assign. And do not copy and paste thousands and thousands of rows of numbers into the docx so the grader would have to scroll through. We don't need to see all of those numbers. It's great, again, to submit your XLS file alongside just to kind of show how you did your work, but the main results, like everything needed for the grading, should be within the actual document that you upload. Okay, so any questions about the homework stuff, about any issues there? I'm also gonna glance online here as I'm wandering. Yeah, in the back. Okay, so the question was about the second problem. So the second problem, I give you a PDF and a CDF. You can ignore the PDF because I already gave you the CDF. And all I'm asking you to do is kind of a mimic of what you did in the first problem, where take that CDF and invert it to generate a random variate generator, but then I don't ask you to generate a histogram. So just invert it and give me the random variate generator. The trick there will be, because there is a square that is involved in the CDF, when you take the inverse, there will be a square root, and square roots are ambiguous. Problem is really meant to be your exercise to see when I'm taking an inverse, when an inverse doesn't strictly exist, can I choose the right parts of the inverse so that I get the range of my random variable right? So the random variable, that the desired random variable, you can, in fact, that's where you can look at the PDF to see where the range of the random variable. And let's say the random variable's range was from -3 to 300. It isn't, but let's say it was. Then when you end up doing your inverse, you'll get a square, when that square root, when you'll do a negative square root, if you were to think about the range that would come out, it may not match -3 to 300. So if you think, well, what do if I do a negative square root or a positive square root, how do I get the right range out? The -3 to 300 range, or whatever the range is, and then you choose that one. So that's really the issue with that second one, is figuring out how to properly choose the right sign.
PDF like incorrect, is it still possible to get like a range like between 0 and 1 for the inverse?
Is it still possible? Well, so so for which one? For the first question. So yeah, so when you're deriving the CDF in the first question, Off the top of my head, I don't remember the exact range of that random variable.
What is the correct?
Oh well, if you do not get the, I guess it depends on, well, yeah. So if you generate random numbers, if the CDF is wrong, then, I mean, all sorts of things could be wrong in your random variate generator. So you could have the wrong range, could have totally the wrong shapes in the frequency distribution. So it's not like, I would say it would be very unlikely for you to get exactly the right range and your CDF to be wrong. Does that answer your question? Okay. Yeah.
So for the histogram, are you saying that we're using the X based on using the random numbers and then put it into the histogram?
Yeah, so for the histogram, you'll generate in Excel, or I guess you could do this in MATLAB or whatever, but you could generate for this R number, that's where you generate the random numbers between 0 and 1. You'll generate this F inverse, which will be the, which will sort of map numbers from 0 to 1 to whatever the range of this number is. That will give you a new column of numbers whose range will not be 0 to 1. It'll be whatever, you know, could be anything. And then you want to histogram that. And so that frequency distribution should look very different than a 0 to 1. Okay. Any other questions about that? And we're going to do an example of this today. So you'll get to see me doing this today as well. So we'll go over this content. All right, questions online about the homework? All right, so I think hopefully pretty clear about the schedule. ICAF is available. Again, that's an ICA that you can take as many times as you like. It's worth like 35 points instead of 10 points. It's a random sample of all the other ICAs. It's meant as midterm practice. So it is due before next lecture. And so it's meant to kind of get you to sort of think about questions that you might ask during next lecture, because next lecture is a midterm review. And so I will have slides that I can go through. They're just samples of slides from all the previous lectures, but I'm totally fine with just plugging in my tablet and working problems if that's what you want to do, or just answering questions. So we can use that time however you like. If things are silent crickets, I've got some prepared material to hopefully get you guys thinking and asking questions or whatever, just kind of hitting the high points that I think of the different lectures that might go over. But that's kind of the plan there. Then next week, Tuesday, Thursday. So next week is the week before fall break. Tuesday, we'll have stage 1. That's the individual exam. It's administered on Canvas. You have to use Respondus Lockdown Browser. Thursday, exact same exam, but it is collaborative, not using Respondus Lockdown Browser. This one's timed. This one is not. And this one, you can use your friends in this class, or not friends, your colleagues in this class. You can use your book, you can use your notes. You can't use other resources. So that's kind of the schedule moving forward. Any questions about the scheduling expectations? Oh, and I should mention, I sent a reminder out to those of you who haven't completed it yet. There is this Respondus Lockdown Browser compliance assignment where pretty much once you have to take it within Respondus, but then once you're in Respondus, you basically just check a box and say submit, and then you get credit for that, which actually goes into a little bit of midterm credit, and that will unlock the midterm unit, unit F2. And inside the midterm unit, there's not only both midterms, which will become available at the appropriate times, but a ton of sample exams from previous years, a practice exam that you can take right now, and some other things too. So make sure to take that as soon as you can to give you access to those resources. So any questions about the schedule? Yeah. Okay. Yes, yes. So that it will give you a grade, but then I think the grade just kind of goes into the ether. And so you can take that as many times as you. And that practice exam is a copy of the exam from last year. And so there are a blank PDF copy of that exam and a solution set PDF of that exam right underneath. I think I saw a hand over here. No? Okay. Anything else? Let me check online. Nothing there. Okay, great. All right, so I'm going to kind of jump ahead to the stuff that we were sort of had to cut off short. So I'm just kind of going through the motivations for this, pseudo-random number generators. And so the big thing that we were ending last time is that we had to test for uniformity and independence. And so uniformity is basically you don't want numbers to clump, you want random numbers to be spread evenly across 0 to 1, and independence, you don't want any patterns. And so even if they're spread evenly across 0 and 1, you don't want to be able to easily just guess the likely distribution of the next number knowing the previous number. And so those are the two things we need to test for. And so we talked about the chi-squared test. So I want to make sure we cover the Kolmogorov-Smirnov test. And so the chi-squared test, we did this example last time, so I'm not going to spend a lot of time on it unless there's questions here. But the chi-squared test, hopefully you've got experience with this, I think either in 380, 385. I always forget what we cover in each of those two classes. But the basic idea here is if I give you a bunch of numbers, I will give you a number of subintervals that you'll divide up the unit interval from 0 to 1, and you divide that up into equal bins, and you count how many of the numbers I gave you went into each bin. And then you ask yourself, how many would I expect to go into each bin if things were uniformly distributed? If they're uniformly distributed, it would be the number of numbers divided by the number of bins. So in this case, it would be 7.5 because I had 30 numbers up here. So there's 30 numbers here. And so there are 4 bins here. So 30 divided by 4 gives me my 7.5 expected number down here. And so here are my observed quantities, 3, 4, 8, and 15. So 3, 4, 8, and 15. And so I can calculate a chi-squared statistic way down here. And the bigger that number, the farther off our sample numbers are from the expectation we get from the null hypothesis they're uniformly distributed. And so there will be a critical value corresponding to our 5% type 1 error rate. And so if we go to the table, and I will give you this table if I give you this type of problem on a midterm, and the degrees of freedom you look up in the table is the number of intervals minus 1. And we'll go into the reasons why that after the midterm when we generalize this test. So I had 4 intervals, so I choose the degrees of freedom of 3, slide on over, and I had an alpha of 0.05, a type 1 error rate of 0.05, and so I get a critical value of 7.81. So because my chi-squared distance was way bigger than 7.81, then these numbers are way different than the null hypothesis. And so we're saying these are not uniformly distributed, or at least they don't look like they're uniformly distributed, and we're pretty confident that we can say that they're not based on that. Any questions about the chi-squared test? Again, hopefully you guys have seen the chi-squared test enough times. One thing I want to emphasize that we will re-emphasize after the exam is that this expected number in each bin, which is 7.5 in this example down here, must be greater than 5 or equal to 5 in order to use the chi-squared test. So 5 is the threshold that you have to look for. If you start doing this test and you see that this number is not greater than or equal to 5, then you either have to modify the chi-squared test in a way we'll talk about after the midterm, or use a totally different test like the one we're about to go over. So that pretty clear? Okay. All right, so what happens if, maybe I'll switch to the other presentation for this one and make sure I hit all of the original steps. Okay, so this is just the original. So yeah, so whenever you hear counts, you could think chi-squared. So we go through the chi-squared stuff like we did last time, same thing. Now, what happens if that expected value is less than 5? If you have too few samples to do a chi-squared test. So you can't use this count-based prediction. You have to come up with a different prediction that uses a different test. And so in that case, instead of counting how many things fall into these subintervals, our approach when we have very few samples is to sort. So if we sort the numbers that we've been given, then you know that each number should be close to kind of its sorting order in the uniform distribution. So if I have 10 numbers, the first number should be close to 1/10. The second number should be close to 2/10. The third number should be close to 3/10, and so on. So if things are really uniformly distributed, when you sort them, they should be close to wherever the kind of their order falls when you divide by the total number of numbers. That's the Kolmogorov Smirnov test in essence. And so the way that looks is if I were giving you a bunch of numbers, this blue column, this RI column up here, this RI row, the blue row, which maybe I'll just, from this angle, it's just maybe easier to do this. These have already been sorted in this middle row here. And so what, I could give these to you out of order, but you would have to put them into sorted order here. And since there are 5 numbers in the list, then we would expect the first number to be relatively close to 1/5 or 0.2. The second number to be relatively close to 2/5. The last number to be relatively close to 1. So what the KS test says is, okay, I'm going to look at the distance of that number to its kind of the order, its order and the order, the previous order. So I'm going to calculate 2 distances. So for this number, how close is it to 1/5 and how close is it to 0? And so I calculate those 2 distances here. So 0.15, that's just 0.2 minus 0.05. 0.05 is just 0.05 minus 0. For the second number, I do the same thing. I say, how close is it to the top number? Well, that's just 0.4 minus 0.14 gives me 0.26, and then the other direction. Now, in this case, 0.14 minus 0.2, that's a negative. Well, the negatives are always going to get squashed by the positives. And so whenever you see that you're going to get a negative here, then we don't even have to calculate it. So sometimes we just leave those out. And then you keep going down through that. So this was one that you've done already. This one I gave you on the homework assignment, the last homework, where it was kind of organized this way. And so you end up getting a bunch of differences, and you take the maximal difference between all of these. And so I look over this whole set of differences, and I see the maximal difference is 0.26. And just like the chi-squared test, this maximal difference is a measure of how far away our sample data are from the null hypothesis. The null hypothesis is kind of like the cumulative distribution of a uniform, which is a diagonal. And so we're saying here that the sort of the sample CDF of the data is this far from the expected CDF. That's kind of what how to interpret this number. The bigger that number, the worse. So we have to look up in a table. So here's the 0.26. And so if I look up in a table, which I would give you on a test, I say for a 0.05 confidence level, and I actually use the actual number of data here. So I don't to take off 1. In the chi-squared, I take off 1 because counts always have to add up to the total count. So once you know 4 counts in a 5 count array, you know the 5th count. That's the reason why it's a 4, even though there's 5 boxes. Here, there's 5 boxes, but I'm not counting up, so I don't lose a degree of freedom by cutting things up this way. That's the reason why I still use a 5. And so I look in my table, and I'll say for 5 degrees of freedom, for an alpha of 0.05, the critical value is 0.565. So I'm going to say, well, 0.565, how does that compare to 0.26? 0.26 is less than 0.565. So I cannot conclude that these numbers are different than uniform. It doesn't mean that they are uniform, but based on the evidence that I have here, I can't say that they're not uniform. Now, as we'll learn after the midterm, the KS test has a high statistical power, which means it's one of the few tests that when it turns out this way, that you actually can have some confidence that you can accept the null. But most of these tests, it's difficult to accept a null. The best you can do is reject it. But in the KS test, it's a pretty good sign that, especially as you get more and more data, that if you can't reject it, then you might be able to actually accept the null with high probability. And we'll talk a lot more about statistical power after the midterm. But for now, all you need to know is you look up this critical value, you compare it. If it's less than it, then it's a thumbs up for your random number generator. If it's greater than it, then it's a thumbs down for your random number generator. Any questions about the Kolmogorov-Smirnov test, the KS test? It's the alternative to the chi-squared when you're using too few samples. When you have a lot of samples, this becomes a pain to calculate, but once you have a lot of samples, the chi-squared test works great. So for small numbers of samples, use this guy. For large number of samples, use the chi-squared. Pretty clear? All right, so let's get into the new ones here. This is just me. Oh yeah, so this is me expanding on that sort of thing. I think I'm going to skip over this kind of background stuff because we will talk about this a lot more after the midterm anyway. All right, so the other tests that we need to cover are the independence tests. And so random number generator has to be uniform and independent. Those are the two requirements of a pseudo-random number generator, uniformity and independence. So how do we test to see if our pseudo-random numbers are independent? Now, there's a bunch of different ways that we can attack this problem. So the general problem's right here. The null hypothesis is that they are independent. Alternative hypothesis is they're not independent. So so I need to have some test of independence. So those tests are going to be built on if they're independent, what would I predict these statistics to be? And so one of the ways I can do that is with a so-called autocorrelation test. Now, this is a test that you're not going to have to do, but I'm going to want you to at least know the word autocorrelation and the general gist of what we mean by an autocorrelation test. But it's a pain in the butt to actually manually do this test. But it's a tool that you will use if you ever do any time series analysis in the future. So the idea here is I've actually got, this is the same set of sampled data points. And so this is 0 to 500 samples. And I've zoomed in on 0 to 50 here. So these are the first 50 samples. These are the whole 500 samples. And so when I look at this, I want to know, are these random numbers independent? In other words, how well can I predict a future number based on a past number by looking at these series here? And so the thought is, well, what if, I know that if I take all of these data and I plot them against each other. So if I were to plot for every sample, I could plot the sample on the x-axis and itself on the y-axis. And if I were to do that, I just plot, x versus x, I'm going to get a diagonal line. And so that diagonal line would mean that if I know the current sample, I can always predict the current sample. Like that's trivially true. So there's 100% correlation between the current sample and itself. Now, what an autocorrelation does is it does that for the current sample and every sample that comes after it. So you could do the autocorrelation test and you could say, for one so-called lag, so I'm going to plot my sample on the x-axis and the next sample on the y-axis, and I'm going to get a scatter plot. And I could fit a line through that scatter plot and get a correlation out of that, a correlation coefficient. And I could plot those correlation coefficients for every single lag. So for 0 lags, I get 100% correlation. So that's the data plotted against themselves. For 1 lag, that's the data plotted against, that's the next data plotted against the previous data that are 1 sample away from each other. I might get 25% correlation. For 2 lags, I might get 10% correlation, and so on. Negative correlations here mean that I can still predict things, but positive numbers previously mean negative numbers later. And for these data, when I do this autocorrelation analysis, I get exactly this plot down here. And so you can see that, that there are certain lags where I actually have high probability of predicting that number. So if I know, if I take some value and I go out to 10 later, I have a decent probability, almost 50%, let's call it 40%, of predicting that number. So I can explain 40% of the variance just by knowing that previous number if I go 10 lags. And so every 10, I end up getting this same predictability. So this shows me that it may not quite look like it when you stare at it because it's got a lot of other noise there, but there is some periodicity in this. And so some of these peaks that you see here are actually separated by 10. And so you're seeing some periodicity, like kind of like a sine wave with noise on top of it right here. And that's what the autocorrelation is telling me. Now it tells me that there are other lags that get much closer to this threshold, this blue threshold, which you can kind of think of as like the 0.05 threshold. Now, if all of my lags are within this blue threshold where really I have no predictability, then I would say that this thing is not correlated with itself. In other words, it's independent. Every sample is independent of the previous sample. But if I have a significant number of these above these blue thresholds, then I can say that this thing lacks independence because I can gain a lot of information about future samples just by knowing previous samples. And so this autocorrelation plot, otherwise known as a correlelogram, which Arena can generate for you, this gives me a lot of information about, just by eyeballing it, about whether a data set is independent or whether there's a lot of predictability buried in that data set. So I just want you to remember this autocorrelation. So that's self-correlation. How well are you correlated with yourself? That's what that autocorrelation is. In principle, this is our motivation for how we would build an independence test, is we would just like to say, how much can we predict about the future from the past? That is what the ideal would be. Are there questions about this sort of test? This is not the test we're going to be using. This is impractical for us to use to get like a simple, is it independent or not? Because you're kind of have to ask the question at each one of these lags and then have to deal with the fact that some of these might be within the threshold and some are without, and what does that mean? So this really ends up just being a heuristic for you to eyeball, but an actual statistically rigorous test is going to have to be a little more clever than this. But does this basically make sense, this correlelogram, where each one of these is studying the correlation of a time series with itself that many lags later? Might be a little abstract, but at least you want you to have some familiarity with this type of plot. Because we'll actually see this come back when we handle batching after the midterm. Okay, so we could do all this sort of stuff. So if we had more time, then I would go ahead and go through some of the math behind how you would do an autocorrelation test. But in the end, we end up deciding that this particular test is just a little too cumbersome. It's a little too cumbersome and problematic. So I'm not going to bother with that right now. And so instead, what we do to test for independence, this is the stuff that a test you should know how to do for the exam, is a so-called runs test. And so we have to think about what's a different prediction we can use to test for independence. And so rather than doing this explicit correlation analysis, what we say is, in the null case of independent data set, how often would I get a string of the same outcome? Like say, if you're flipping a coin, how often would I get heads over and over and over again, like a run of heads, if I assumed every coin flip was independent of every other coin flip? I can use that to generate a distribution of runs. And if my actual distribution of runs differs from that distribution, then I conclude that my whole data set is not independent. And so, and that's kind of what we're just motivating here. So how do we do a runs test? Well, we take continuous data that we get and we convert it into binary data, zeros and ones, ups and downs, heads and tails, coin flips. How do we do that? We're going to basically say, well, what's the mean of these data, or what's the median of these data? And then ask how many data are greater than the mean and how many are less than the mean. The ones that are greater than the mean, we're going to replace with a 1. The ones that are less than the mean, we're going to replace with a 0. So any data set, any continuous data set we get, we can replace with a binary data set of zeros and ones. And then we can ask what's the probability of runs, like I said, for the coin flip, so we get for this new 0, 1 sequence. And so we're going to use a so-called runs above and below test. There is another test called a runs up and down test. In the past, other people who've taught this class decided to use the runs up and down test. I like the above and below because it's a simpler test to teach, and it's very similar. I've had students who I think got midterms from other professors from 10 years ago who came into my class and for the midterm and would do a runs up and down test on the midterm, even though I didn't teach it. and then they would get the wrong answer. And so back then, that's when I was hand grading all of the exams. And so it's clear they were doing a test that I didn't teach. The only way they could have learned it is if they were just studying old midterms. And so that's just kind of a warning that there are other tests out there. A runs up and down test is another popular runs test, but we do the runs above and below test. It's a different type of test, but it's very similar, but it's done very, like the numerics are totally different. So let's just see how it works. And so this is kind of going through the steps here. We'll go through an example here because it'll make a lot more sense me reading out these steps. I will say that like in MATLAB, there's a runs test command that does all this for you. So you have to know how to do it once, kind of by hand. But then after that, if you ever need to do a runs test, then pretty much any numerical package is going to have a runs test already built into it. Okay, so how do we do the runs test? So like I said, we take all of our data set, which are going to be continuous data from 0 to 100 or whatever, including pi or whatever. We can calculate the average of that runs test. If I did this on a midterm, I would give you the average, so you don't have to worry about calculating it right. And then you can ask whether each sample is above or below the mean, or you can use the median. That's just as fine as well. And then I can then put those into two numbers, the number above the mean, the number below the mean, just a count of those two. And then I can then say, all right, now that I have them all converted into above or below, then let's see how many runs I get. Now, I'll show you what a run is more concretely, but it's a continuous string of the same outcome. So if I get above, 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 below, above, 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 that would be 3 runs, because the above, above, above is one run. Below, that's another run. Above, 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 that's another run. So that's 3 runs, because there's just, it's whenever it switches, that's when a run changes. So how many runs do I get? And if independent, then there's, I actually know that the distribution of runs should be normally distributed. And that normal distribution will have this mean and this variance. So these are good formulas to know. So you might want to copy these ones down. So these will be formulas that if I know these, this is under the independent assumption. This is exactly what I would need to describe the distribution of runs I should get. So once I know this, which are parameters of a normal distribution, and I know the actual number of runs are in my data set, then I can use a z-test. So basically calculate a z-score to be my statistical test on independence. And so I can say, what's the number of runs I get minus the average number of runs I expect under independence, divided by the standard deviation that I would expect under independence. And if the absolute value of that number is greater than the z value from the z table for the z-test with alpha divided by 2, because it's a two-tailed test, then I know that I violate independence. So let's just see an example of that, and then I can ask for questions. So we've got a data set here. The question is, are these numbers independent? So with all of these, I could go through and I could calculate the mean of those. And I would give you a mean on a midterm. And it happens to be 0.676. So that's just the mean here. So I could go through every single number and I can convert them into below the mean, 0, or above the mean, 1. So 0.18 is below the mean, so it gets a 0. 0.38 below the mean gets a 0. Then 0.86 above the mean gets a 1. So I convert them all into 0s and 1s. So from here, I can then count the numbers of 0s and 1s. The number of 0s is the number below, the number of 1s, the number above. So the number above, there's 17 above. The number below, 13. Sanity check, 17 plus 13 is 30. 30 numbers. So I did my counts maybe right. And then I can calculate the number of runs in this sequence. What does that look like? Well, I've broken it all out. Here's the same sequence here. And I broke out each of the 19 runs. So the 0, 0, that's a run. The single 1, that's a run. The next 0, 0, that's a run, all the way down through to 19. So I'm going to leave this up here for a second. Are there questions about where I got these runs? It's pretty clear how I calculated there are 19 runs in this 30 number sequence.
2 in a row counts as a run?
One in a row counts as a run, but a run is terminated when it switches. So it's almost like how many times does it switch? But maybe like it's one off that, I guess. How many times it switches? Yeah. The top, or where did I get that? Each one of these, if I go back to my data set back here, it's these 30 numbers turned into 0 if the number is below the mean and 1 if it's above. So 0, 0, 1 corresponds to below, below, above. Does that make sense? Any other questions? All right, so now I have enough information. Just gonna double check there's no questions online. Okay. So now I have enough information for me to do, yeah, I'm sorry, go ahead. Yes, exactly. Any other questions? Good. All right, so now that I know these 3 numbers, I can now test whether this string of numbers is likely drawn independent from each other. And so I then, from these 2 numbers here, in A and in B, can calculate under the null hypothesis, if these are independent, then given that there are 17 above and 13 below, I would expect an average number of runs under independence of 15.7. Under independence, given there are 17 above and 13 below, I would expect a variance of 6.9772. So I'm not going to derive this, but you can derive this using the Bernoulli trials that we talked about before. You can derive this normal distribution. So this is the normal distribution that I would expect in numbers of runs if they were independent. So from there, I have to remember, take the square root of the standard deviation, or sorry, the square root of the variance to get the standard deviation. And I can calculate the z-score of the number of runs that I actually got. And so I received 19 runs. I expected 15.7. I'm going to divide that by the standard deviation, which is the square root of 6.9772. Remember that square root, it's really important. And that gives me a z-score of 1.2367. So is that z-score, if that number is really big, then that means this is far from independence. If that number is small, then these might be independent. So I'm going to look in my standard normal critical values. And for an alpha of 0.05, I have to remember to divide that by 2 because it's a 2-tailed test. And so it's 0.025 is my critical alpha. And that corresponds to a number 1.96. And over time, as you do more and more stats, 1.96 will get burned into your mind because it shows up over and over and over again because it's such an important critical value. So 1.96, I compare that to the 1.2367, and 1.2367 is less than 1.96. And so we do not reject the hypothesis of independence. So it may be safe for us to call these independent. Questions about the runs test? Is that pretty clear? Questions online? Okay. All right, so and that is the only test that you have to worry about. So we have 2 tests that you have to know how to do by yourself for uniformity, chi-squared and Kolmogorov Smirnov. 1 test you have to know how to do on your own, the runs above and below test. And then also you need to know roughly what autocorrelation means. So an autocorrelation or a correlelogram is a diagram that tells you how correlated a sequence is or series is with that same series that many lags later. All right, so any questions about those 4 concepts? Okay. All right, so the last thing that I want to then cover today is this new stuff that we talked about on the the homework. And so I have a couple other slides in here about the pseudo-random number generator. Hopefully, if there are any questions about that, definitely happy to take them on Thursday when we go through review. And so, yeah, so the question here, so what do the new stuff that we want to add on today? So in Arena, you decide you drop a process block, you drill into the process block, you get a box that looks something like this. And in that, that block down here, you're going to have to decide how long things stay in this process block. And this is where those input models come into play. And there are a bunch of expressions that they've already preloaded in for you down here under delay type. And unfortunately, they use the term delay, but you know it's inactivity in this case. But and so we can choose one of the ones already given us, or we can just say expression, and then we can type it in ourselves down. And so we can type in the expressions they've given us, but a lot of times we're not going to know, it won't fall into one of the stock ones that they've given us. And so we have to come up with our own expression. And so then the question is, how do we come up with that expression? And so this expression down here, 4 minus 2 times unif 0, 1 plus 2, we've already kind of learned how to do that back in the lab, the Monte Carlo lab. You say, oh, well, that's the formula that gives me a uniformly distributed random variable between 2 and 4. But how do we come up with those expressions in general for any distribution? That's what we're doing today. And that is also the subject of that homework that's out, D2. And the idea here is if I've got a CDF there's CDF up there, then I take that CDF, which is plotted down here, and I invert it so that I kind of use the y-axis as the input and the x-axis as the output. And then I can push in uniformly distributed random numbers and get random variates out. And this is inverse transform sampling. So that's all I was saying here. I give you a PDF. You can solve for the CDF. Once you know the CDF, you can solve for the inverse CDF. Now, how do you do that in general? If you have the CDF, f of x here, then that CDF here, you can set it equal to r. So you have r on the left-hand side and x, an expression of x on the right, and then solve for x. So that you'll get x on the left-hand side and some expression of r on the right-hand side. And that will be your random variate generator. And then once you have that random variate generator, then you go into a program like Excel and you generate a bunch of numbers between 0 and 1, uniformly distributed, a bunch of random numbers, and you plug them into that expression that you just found. And the x's that you get out should be distributed like the random variate that you would like to work with. So here's an example, a kind of a simple example for the exponential. So here's an exponential PDF, probability density function. I need to find the CDF. So this is what I do in general is I integrate this PDF from negative infinity to x. So f of x is negative infinity to x. And this technically is piecewise because it's 0 up to 0, and then it finally gets some density after 0. So I'm going to break it into 2 pieces. So, so basically the first piece is the standard CDF definition that you're familiar with, negative infinity to x with the f of t, but this only goes for x's less than 0. At the break here, then you have to break your definite integral up so that it goes from negative infinity to 0 with the first piece, with this piece up here, and then add in the rest of the integral from 0 to x for the bottom piece. And so this is the way you get negative infinity to x when x crosses one of these boundaries. So this is our general form here. And now we can just plug in the 0 into the blue parts here and the lambda e to the lambda x into the red part here. If I do that, then I get this thing down here, and then I can solve each of these 3 little integrals separately. And there are 3 totally different integrals because this one is an integral up to x, This is integral of the whole range from negative infinity to 0. So this is a constant. This is not necessarily a constant. This definitely is a constant. And this is the variable from 0 to x. So then I can do that. This integral is 0. This integral here happens to also be 0. And this integral is 1 minus e to the lambda x. And I think in the next slide, I have a little inset that if you forgot how to take an integral of this, then I show kind of how to do that with some substitutions up here. But the main point is down here. So this is how you get from this piecewise PDF to this piecewise CDF. Now we're going to do a more complicated one, but this is just a warm up. Are there questions about the steps here? This one doesn't seem like, I mean, it really just seems like I just integrated it. You know, I took an integral at the top, an integral in the bottom, and I did them independently. And that's just because the top was all 0. But I do it this way. It's a little pedantic to do it this way but I'm trying to show that actually, though, generally, we have to carry along with us everything that we've done in the previous steps of these piecewise PDFs. Okay. All right, so let's see then. So we've got our CDF down here. And so how do we then find the inverse transform how do we generate the random variate generator? So I need to solve for the inverse of this PDF. So I'm going to set R equal to the portion of the CDF that are non-constant. So you basically throw out all the portions of the CDF that are constant. In other ways, you throw out parts of the range in the PDF that are 0. And so in this case, there's only one piece left over that has non-constant CDF or non-zero PDF, and that's this 1 minus e to the lambda x part. So then I set R equal to that, and then I solve for x. And that's all I'm doing over here, is solving for x. And so I end up getting this thing here. This x equals minus 1 over lambda, natural log 1 over r, or 1 minus r. And that there, I can just swap out the x and put in my inverse CDF symbol. And there I've got my inverse CDF, otherwise known as a quantile function. And from there, I could just drop in values of r from 0 to 1, and I would end up getting exponentials out the other side. Now, in most practical scenarios, whenever you see a 1 minus r, you replace it with just an r, because r is distributed from 0 to 1 uniformly, so is 1 minus r. So whenever you see a 1 minus r, the optimization that is usually done is you just replace all the 1 minus r's with r. Because if you're going to generate a million random numbers in a simulation, getting rid of a little bit of arithmetic actually can shave some of your simulation time down. So whenever you see the 1 minus r, you will swap it out. On a midterm, I'm not going to ask you to do any of those optimizations. On a midterm, forget about this. I put it up here because the book mentions it. And in practice, if you ever look up an exponential generator, you'll find this formula down here. And that's because they do this optimization. But for now, at this point in our careers, we don't worry about this optimization, and we just do this formula up here with all the 1 minuses left. So questions about this inverse step to clear what we've done. Questions online about the inverse. All right, so once I have that inverse transform generator, then I can go in and generate a bunch of uniformly distributed random numbers between 0 and 1. You can think of this as one column in Excel or Google Sheets. And then you plug it into that formula from the previous slide, and you get another column out. And although this column goes from 0 to 1, this column will go from 0 to infinity. If I take a histogram of this column here, then I end up getting these red bars here, which if I were to overlay with appropriate scaling, the PDF on top of it, then it lands right on top of those bars. And I didn't ask you to overlay these PDFs on the homework. It's a little more advanced to know how to properly scale these things. But if you were to, then it lands right on top of that. So the histogram approximates the PDF, the density function. So questions about that? It's pretty clear. Before we work on a slightly more complicated example that looks more like your homework example. Okay. All right, so your homework example looks more like this one. It's a piecewise PDF, probability density function. So it's got 0, a non-constant component, a non-constant component, and then another 0. So we know the triangular distribution is only, it's supported such that it gets this triangular shape only from A to B with a mode at C. So that's what we've drawn out here. And we should expect to get an S-shaped CDF that looks like this, where it's 0 until it's A, climbs up, hits an inflection point at the mode, flips the other way, and then becomes 1 exactly at B, and then is 1 on that point on. So we want to derive this. So how do we do that? Well, this is the general format for this thing. And so I have 4 pieces of the PDF. So I can write 4 pieces of the CDF in this kind of triangular form. It's not a triangular form because of the triangular distribution, they're just always going to look like this. And the first piece is going to look like a normal, a standard, I don't want to use loaded terms here. This is going to look like your conventional cumulative distribution function, negative infinity to x, and that goes only for the range corresponding to the first piece. The tricky part then is at every next piece, then you get a constant component from the previous piece. So it's just all of the previous pieces, but constant because they go across the whole range for the previous piece, plus the marginal increment from the current piece, which will be from the end of the last piece to x. And then I can do that up. So there are questions about this structure here, how I break it into 4 pieces, and then each piece gets broken up so that the 4th piece itself has 4 pieces. Is that pretty clear? This is the general formula you can use on anything, including your homework. So once you have this, we can swap in the values. And so these blue ones are all going to get a 0. These magenta ones are all going to get that. These green ones are also going to do that. And the red one is going to get that. I can swap in the values and then solve each one of these definite integrals separately, and then simplify algebraically what results. And so I swap in the zeros. So all of these are going to be 0. The magenta piece, I'm going to swap in the magenta piece and the green piece. And then this 0 is going to be 0. I already put that in to be just because it's easy. So I can take this integral, or these integrals, and these integrals. Notice this integral is variable. These are constant. This integral is variable. This one's constant because there's an x as the upper limit here, but a b there. There's an x as the upper limit here, but a c there and a c there. And so after I do that, then this is what I get when that integral, that magenta integral is variable. This is what I get when it's constant. Likewise with the green. And now I just algebraically combine all those things together, and voila, Bob's your uncle. That is the S-shaped CDF that I was expecting. On a midterm, I might now ask you, because I've got this multiple choice, evaluate the CDF at a particular value. And I might ask you for that number, so you could type it in, or I might give you a set of numbers, and you could select it. So that's how I might have you to test you on this on a midterm. That's how I might do a derivation of a CDF on a midterm. All right, so questions about how we got here. Notice it starts at 0, like all good CDFs do. It ends at 1, like all CDFs do. And it's monotonically increasing throughout it. And so at no point do I jump from one value of x to another and the CDF drops. It's constantly constant or climbing. This one here, that is in part of the algebraic stuff. So if I go from, if I were to take this here, if I were to simplify this, I'm going to have to end up, because there's a b minus a here and a b minus a here. if I multiply b minus a here, then combine the numerators, then what I'm going to end up getting is a b minus c over here, and then so you end up getting a 1. Any other questions? Okay. So now we've got the CDF, that's half the battle. So we take our nice triangular CDF and we want to generate triangular values. So we need to invert that CDF. And so I'm going to take this CDF here and I look at it, and there's only 2 ranges that really matter to me. And those are the 2 ranges that are non-constant. And so that's these 2 ranges here, the range from A to C and C to B. So from A to C, if I plug in x equals A all the way through x equals C, I get CDF values from 0 to this value. If I then plug in x equals C into this row and x equals B into this row, then I get output from the f of x that's this value all the way up to 1. So, so these are the ranges that I care about and what they map to. The inverse CDF is going to map these back to these ranges. So for the inverse CDF, I'm going to set R equal to f of x for both of these on both of these ranges, and then solve so that I can get the x equals version of this that will map the r's back to the x's. So let's see how we do this. And so I kind of do this in parallel here on this slide. So the blue ones you can think of as doing it for the top piece in sequence, and then the red ones is doing it for the bottom piece in sequence. And so for the top piece, I say I'm going to set R equal to, if I were to go back here, this part, I'm just setting R equal to this part here for x from A to C. And I know that x from A to C corresponds to this R range. So I then go here and I say, well, if I set R equal to this for this x range, then I can then go through and try to solve for x out of this. And so I do a little bit of algebra here. And what I end up getting here is, after rearranging, x is equal to this thing. And then the range that I'm looking for is that range that I derived from that last slide. So this is the R range that corresponds to that. And I can do the same for the red piece. Set R equal to this red piece, solve, do some cross multiplying, etc. Solve out for x, and I get this piece down here for the R range that I talked about on the other one. So these ranges I had to explicitly choose based on where the x's and r's map to each other, and I could get that from this previous slide by plugging in the x ranges and seeing what R ranges came out. And so this is the flip of that. The one thing that I didn't talk about yet is that the choice of these pluses and minuses, because there's a square that shows up in these expressions here in this system of equations, then I need to choose what sign of the square root. And I chose these signs, a plus here and a minus here, to ensure that when I plug in these R values, the X values come out in the right ranges. If I were to choose a minus there, then this wouldn't be the right X range. If I were to choose a plus there, then this wouldn't be the right X range corresponding to these R ranges. All right, so questions about that? The inverse with a square. A lot of little things that can trip you up, but are necessary to generate these generators. Checking questions online. So somebody asked, how do we show our work for the midterm on this? And I think I already answered that. So the idea would be, if you derived this sort of thing, then I would then maybe ask you, all right, once you've done this, here is a random number between 0 and 1. What would be the corresponding random variate that you would get if you derived this? And I would probably break it up. So I probably would have you do a PDF to CDF on one question, and then an inverse CDF on another question, so that there wasn't, it wasn't like a cascade of errors that would end up causing things to go wrong. I could also ask you for aspects of this. Like I could give you a part of the inverse transform and I'd ask you for what should the sign be here, a plus or a minus, or what, something's missing here, fill it in. So there's a couple of different things that I could do. All right, any other questions? All right. So if I plug in random numbers between 0 and 1, like you do on the homework, I then get a histogram of outcomes out. And if I know how to scale the probability density function, it lands right on top of them, showing me that my triangular distribution works out. So all that's good. Now in ARENA, fortunately, the triangular distribution is one that they have already given us. So we can generate triangular distributed values without this ugly formula that we derived over here. So just a reminder, ugly formula. Now, if we wanted to, we could implement that ugly formula in ARENA. The way it would look like that is I could generate, say, a box like this, a sign box here, and in it, I could assign a variable r to a random number a random number between 0 and 1. And then I'm going to zoom in on this. I could then assign, once I know that number r has been fixed, then I can assign to a variable called triangular sample this really ugly expression, which basically says when r is sufficiently low, use this expression of r. When r is sufficiently high, use this expression for r. So in theory, you could put these complicated piecewise expressions into ARENA. Fortunately, for the triangular distribution, it's already done for you. But if you had to put in one of these piecewise expressions into ARENA, this is one way you could do it, by assigning a random number to a variable, and then because it runs these things in order, then assigning an expression of that variable to another thing, another variable, and then that variable would be drawn every time you run the simulation according to the desired distribution. Okay. All I'm kind of summarizing here is that just like the triangular function, we already kind of know the quantile function ahead of time. If you were to look up distributions on Wikipedia, for example, these are ones from the book, then you can actually find quantile functions, also known as inverse CDFs, already derived for you. So all of the major distributions that have an analytical quantile function, you can already find those written out for you. So if you ever in Excel, like say, man, I really need to draw a Weibull distribution, but I don't want to go through the hassle of figuring out what that inverse transform generator is, just go to Wikipedia, look up Weibull distribution, go to the little quick info on the right-hand side, look up quantile function. And the quantile function will pop out as this expression here. And then you say, okay, I'm going to drop that into Excel. I'm going to drop random numbers into the R spot there, and I will get Weibull distributed numbers out. So, look for, whenever possible, try not to do extra work that you can accidentally, drop ones and things like that, and just look for the work that's already been done for you. And the keyword here is quantile function, or sometimes inverse CDF. Either one of those will work, but these are usually already drawn for all of the standard distributions you might use. So these four and a whole lot more. So that's all I'm trying to state here. All right, so any questions about that? That's the bulk of the of your homework D2. So hopefully that helped bring us up to date on homework D2. So I've got a few more things I want to cover here just for exposure, but these are the main things I want you to know. This is pretty much where the main midterm content ends, at this slide right here. The rest of it is stuff we need to know moving forward, but the stuff I'm going to test you on is primarily ends pretty much right there, being able to derive things like that. So I'll let that stew a little bit. No extra questions online. Let's do a attendance question. And the question I think I'll ask here is, what is another name for the inverse CDF in general? So I just said that if you ever need to look up an inverse CDF because you want to do an inverse transform to generate random numbers in Excel and MATLAB or whatever, and you don't have that distribution out there, then what do? You can look up, and this is the term that you will often find on the Wikipedias, the stats textbooks, or whatever. So what is another word for inverse CDF? Okay. All right, so what I want to close with here is what about those special distributions where it's actually impossible to derive an analytical version of the inverse CDF? So one of those is like a discrete random number. So so actually this might be kind of, we might see this next couple of slides midtermish as well. So for discrete distributions, which you already kind of talked about, I give you probability mass functions, and I don't necessarily have an analytical form here, but I can derive a discrete cumulative distribution function. And if I were to plot the cumulative distribution function, there is an analog to the inverse. So I can graphically flip this thing around. And if I graphically invert that just by flipping it across the diagonal, then if I draw numbers between 0 and 1, then this graph tells me what outcomes I need here. And so, so with this here, for this discrete here, then what this really tells me is the CDF gives me boundaries of intervals for the random numbers that correspond to each outcome. And so for this particular case here, my CDF is 0.2, 0.71. So this tells me that anything from 0 to 0.2 inclusive goes to the first outcome. Anything from excluding 0.2 but up to 0.7 inclusive goes to the second outcome. And anything excluding 0.7 but up to and including 1.0 is the third outcome. And this is how I get any discrete one. So this is something that I could give you on a midterm as well, something along these lines. Now, how do I specify that cleanly inside a program like Arena? Because it's a pain in the butt to do these if-then statements in Arena. Well, Arena has a nice function called disc for discrete. And you basically list the inverse CDF as the arguments to discrete. So discrete takes the CDF of the outcome value, then the outcome, and then that for every single outcome down the list here. So for this particular case, I know that outcome 1 has a CDF value of 0.2. So I do disc 0.21. And then outcome 2 has a CDF value of 0.7. So then I do 0.72. And then outcome 3 has a CDF value of 1.0. So I do 1.03. So that tells me that the disc values will always end with a pair that has 1.0, comma, whatever the outcome is going to be. And these numbers will always be increasing. If you try to give disc non-increasing numbers here, then it will throw an error. And so a lot of people initially, when they put disc in, they try to put the probability mass functions in. If you try to put this PMF, it would see the 0.2, 0.5, 0.3, and it would say, oh, going from 0.5 to 0.3 is a decrease. You can't do that with disc. And so it would throw an error, and you know that, okay, I need to put the CDF in here, and it needs to end in 1.0. So this is how you encode a discrete cumulative distribution function inside Arena, is with this disc function. Questions about that, the encoding from going from here to there? Okay, now, what if I don't have the actual desired frequencies? I just have a data set that is discrete. So I look at a data, well, it's not necessarily discrete, I just have a data set. And so I want my Arena to draw numbers like my data set, but I could not come up with a good analytical model. And so what can I do? One of the things you can do is actually have Arena mimic the frequencies in your actual data set. So what you can do is you can sort the samples like we did with the Kolmogorov Smirnov test. And once they're sorted, you can plot them so that every sample is on the x-axis and its rank in the sorting divided by the total number of samples is on the y-axis. And this is a so-called sample or empirical CDF. Because if you were to plot that, it's going to give you, and I think I've got an example of that here. If you were to plot that, then it gives you an approximation of what the CDF of these data might look like. Here I've got these samples, 0.4, 0.95, 0.25, 0.35, 0.8. I sorted them all, and then I plotted them against their rank here. So 0.25 is first in the order, and there's 5 of them, so that's why it's plotted against 1/5. And then the next one is 0.35. Well, it's second in the order. That's why I've plotted it against 2/5, and so on. And so this here gives me the rough shape of the CDF that these are likely from. It's sort of an approximate CDF for these things. If I were to write that out, it would look like this, where my observed outcomes are in the top row. My probability mass function is 1/n uniformly across all of them. And my CDF is 1/n, 2/n, all the way up to 1. And so I'm just, again, plotting this kind of approximate CDF. So from these data, even if I don't have a CDF, I can pretend like it's a discrete probability mass function with these 5 outcomes. And so I could draw samples from this discrete probability mass function in the same way. So I can go into ARENA and I can then plug in into disk 1/n first outcome, 2/n second outcome, all the way up to 1.0 last outcome. And it will then draw numbers randomly so that they match the frequencies of the numbers that I've observed in my data set. So that's one thing that I can do here. And so the issue with this, though, is that I will only get the numbers that I observed in my data set out. So I won't get anything in between. So sometimes that's not the desired thing, because you said I happen to draw 100 samples, but I want the frequencies to be roughly the data set that I got, but I want other numbers to come up as well. And so what ARENA also provides for us is something called cont for continuous. And what it basically does is it takes our approximate CDF here, and it's going to draw lines through it, and then draw numbers according to that CDF. So I can define a minimum value here, corresponded to 0 probability. And then I've got all the rest of these here. And then this continuous approximation, I can draw from, and then I get data which goes from my minimum value to the highest value I saw in my data set. And the frequencies are a little higher in some regions, a little lower in other regions that are drawn from the data. So this is an example of a data-driven way for us to draw random variables without coming up with a model first. It's always better to come up with a model that's reduced parameters, because you don't really know how generalizable these data are that you took. But if you really can't come up with a good model, then this is a good worst case option. So I want to make sure you hit that too. I think that then the other thing that you possibly can do is if you do give a probability mass function in terms of a formula, it is possible to write these intervals algebraically. And if you're clever, you can come up with an inverse transform generator like this one that has a closed form. So that's the other kind of example I'm doing here. This is, again, just an example of if you are given a probability mass function with an analytical PMS, sometimes it's possible to come up with an analytical inverse transform as well. So I think that's all of the rest of the stuff was bonus. If we had time, I'm not really worried about it here. So what I'll do is I'm gonna give you the last attendance question. And if there are any questions, I'm happy to take them. Otherwise, all of Thursday will be about exam review. So I'm happy to take any questions you want then. So our last attendance question for today is, what is the command in ARENA, or the name of the command? What is just the name of the command in ARENA used to draw discrete random variates? So I said there's a command in ARENA that allows you to encode a cumulative distribution function into it. so that Arena will draw discrete outcomes for you for arbitrary discrete random variables. What is the name of that? That's all I got for you today. I guess I'll move forward to that attendance slide there. So feel free to ask questions. Otherwise, see you Thursday for the midterm review. Sure. I think I'm not getting here. Let me just close down here. All right, if there are no questions from online, then I'm going to go ahead and end the session for today, and we'll see everybody Thursday.